Alright, so the next problem that we're going to talk about is problem 28. So we have again a finite a plastic rod of finite length which is uniformly charged as well, and this P2 point, right, is again on top of one of the end, okay, and there is a P1 point, alright, and the P1 point lies along on the line on which the charged rod lies along as well. So there are 2 points, and this figure, as you can see, is applicable for problem 28, 33, 38, 40. For us, we are now dealing with 28, and this one only involves P1. Alright, so if you remember the previous problem we talked about, that is problem 26, I guess. This problem should be less complicated compared to the previous one. So I think at this stage we all know what to do. So capital Q is given, L is given, and D is given, right? So where have we been? So here it is, right? And then of course we're talking about problem 28, and we're continuing chapter 24, of course. 24. So that's the rod. That's the rod of length L plus, and that's D. Question is, what is the potential at D? And capital Q is given, so lambda equal to capital Q divided by L, the linear charge density, and of course the distance. So this is point P. Let me choose another color to indicate the distance of the source from point P. So this should be small l, and this small segment at a distance small l should be dl. So therefore dq should be equal to lambda times dl. So v equals 1 by 4 pi epsilon naught integral over dq divided by r. In this case it's the distance L. So what is it going to be? Well, we have lambda divided by 4 pi epsilon naught. Lambda comes from dq, and we have L to the power -1 dl. And what are the limits? The limits are so the lower limit starts from this end, which is at distance d from the point P, and the upper limit should be d plus capital L. I think this is a pretty straightforward integration. 4 pi epsilon naught, and then we have L to the power this is L to the power -1, so if you integrate over it you should get a logarithm of L, right? That's what we should get. And of course I'm going to put on absolute value around L, because that's the rule. That's what a sane person, a knowledgeable person should do. So 4 pi epsilon naught log of d plus L minus log of d. If you simplify it further, then you should find 4 pi epsilon naught log of d plus L divided by d. So that's the answer. Plug in the values, see what number the calculator spits out, and this is going to be the answer. So easy, right? Well, let's move on to number 43, because that's in our suggestion. So that's 43. What do we have here? Well, we have plus q, minus q, plus q, minus q. 4 charges on the 4 vertices of a square of side length a. Alright. How much work is required to set up the arrangement of the figure? And the particles are initially infinitely far apart and at rest. So if they were initially infinitely far apart, there were no interaction, and the potential energy, not the potential energy is 0. So always remember this, that, well, I should better write it down. So that's 43. How should I draw this? I should just draw it by hand, right? So like that. So assume these are straight lines. So this is plus q, plus q. This is minus q, minus q. So that's the squares and the charges, and each side is of course a. The question is, what should be the potential energy? So when we're talking about energy, we're talking about U. And remember, the difference in U divided by Q, the charge we'll be talking about, will give us the change in potential. Right? The change in potential. Now, when we talk about the potential, we will always talk about a function defined in 2 points, and if you take one of the points to be 0, one of the point to be of 0 potential, then the other point will be the sole determinant of the function. Of course, charge plays a role in, but it's not all the charges. If you consider about all the charges, then you need to think about energy, because whenever you think about a configuration, charge configuration, a complete charge configuration, then you always can associate an energy with it. Alright. And for example, here we have been asked, what is the energy required to assemble this configuration? So initially, these charges, let me use a different color, these charges were all at infinity. That means they're infinitely far away, and then they have been brought back. So this was the infinity was their initial position, right? And these are the final position. The question is, what's the net amount of work? Alright, let's see. So when they were infinitely far away, then of course their energy, it required no energy to send them far away, so that should be 0. Okay, what about the energy to bring them to their final position? Okay, so that simply is going to be, every term should have 1 divided by 4 pi epsilon naught, and then I should have q, qij divided by rij, and I cannot be equal to j, right? So that's excluded, right? So what's the energy required, or energy being stored in this case, to from working for or against the electrostatic field to assemble these things? So if I break it down, what should I get? I should get U equal to 1 by 4 pi epsilon naught, and then I have So let me give them some names. So this would be Q1, this would be Q2, this would be Q4, this would be Q3. So you can see, if I talk about, for example, Q1, right, then first you bring in Q1, so nobody was here, everybody was infinity. Then you bring in Q1 to its place, right? Then you bring in Q2, then you have to work against, or work, the electrostatic force has to work, right? Whether it's positive or negative, that would be determined by the signs of the charges. But it has to work in the presence of Q1. So you have Q1, Q2, divided by the distance in between, which is A. Alright, so now that Q1 is here, right, and Q2 is here, you have to bring in Q3. So you have Q1, Q3, right, divided by, well, now it's not A, it's square root of 2A, because it's this distance right here. But it also, the Q3 also has to work due to the presence of Q2 as well. So Q1, Q2, I'm sorry, Q2 to Q3 divided by A. Okay? Alright, so now you have Q1, Q2, Q3. Now you have to bring in Q4. So what would it be? So you have consider Q1. So you have Q1, Q4 divided by A. You have to consider Q2. So you have Q2, Q4 divided by, well, that's the distance, right, from Q2 to square root of 2A. And of course you have to consider Q3. So Q2, Q3 divided by A. Right? So as you can see, naturally we have considered all the terms. But if you look at this term, this statement right here, if I is not equal to J, then if I has 4 possibilities, for each possibility J has 3 other possibilities. Because if I take Q1, then I have to take all the other charges except for Q1, right? But then as we can see here, once you have taken the combination Q1, Q2, you don't take it back again when you are considering Q2, right? So that if we did that, then we would have double these terms, but we don't have to, because it's already been considered once you have taken Q1 and Q2, right? The energy that has been expanded to bring Q2 here, we don't have to consider reverse combination, because that is unphysical, right? You don't, once you have brought Q2 here, then you do not consider what would be the energy to bring Q1 in the presence of Q2, because Q1 was at its position from the beginning. Q2 came later. That's the serial we considered. We could have taken the otherwise as well. Then the first combination would be unphysical. Do you understand? We're maintaining the physicality of the situation, right? Not just mathematical symmetry. So therefore, I'll have to impose another condition, which is I has to be greater than J, or J has to be greater than I. You could have chosen that. That would be fine. So that cuts down almost half of this term. Okay. So there, if I don't impose this condition right here, there would be 12 terms here, right? Because you have to consider all 4 charges, and for each charges you have to consider 3 other charges, so that would be 12. But we have 6. Why? Because once you have taken this combination, you do not take Q2, Q1 combination. So you maintain that. And if you notice that one of these terms is bigger and the other is smaller. Okay, so this would be then the I, this would be then J. I, J. Why? Because I has to be bigger. I, J. I, J. I, J. I, J. See? J, I is always bigger. So I is the latter one. Do you understand? I should have written JI here. So I, J. Yeah, that would be much more consistent, but it doesn't matter really because it's just indices. So I, J, J, I. Anyway, so I think you have got the point, and you just plug in the numbers and you'll get the result. Okay, so should we simplify it further for you? I think it's very easy. So notice everyone has these A's, right? So I should take away these circles. So 1 by 4 pi epsilon naught. Okay, so as we can see here, Q2 and Q4 are negative. So we have negative Q squared divided by A. So I'm taking A outside. Plus, this 2 has to be positive, plus Q squared by root 2. Q2, Q3, again, negative. Q squared. Q1, Q4. So again, negative. We have minus Q squared. Q2, Q4. What would that be? If it was Q2 is negative, Q4 is negative, so it would be positive. So Q squared divided by root 2. And Q2, Q3 would be negative, so we have Q squared divided by 1 with a negative sign. So how many negatives? 1, 2, 3, 4. I have 4 of these negative terms. So that would be 4Q squared and 2 of these positive terms plus root 2Q squared. So minus 4 plus root 2. So that's it, right? You have root 2 minus 4 Q squared divided by 4 pi epsilon naught A, and then you just plug in the values for Q squared and A, and that will give you a number, and that would be the answer. It's that easy. But remember, the tricky part is to take these combinations here. Alright? And if you think about first bringing in Q1, then there is no charge here, and so it doesn't have to work. Then in the presence of Q1, you bring in Q2, you find the work due to that. Then in the presence of Q1 and Q2, you bring Q3. So the work due to the presence of Q1 and Q2 both. And then in the presence of these 3 charges, you bring in Q4. So yes, you first find out the work due to the presence of Q1, then Q2, then Q3. Do you understand? That's the process you should follow in general. And that's the safest way as well. Alright, next problem. Okay, so here is 50. That's the next problem in the suggested list. How much work, there is a figure, I'll go to the figure a bit later. How much work must we do to bring a particle of charge q? So the particle that you are bringing to a certain point, that particle's charge is given, and the particle's initially at rest along a dashed line. Okay, so let's go and see the figure. Where is it? 50, right? Yeah. So this charge, right? So it has been brought. It was at rest at infinity. It was brought to the indicated point near the two fixed particles. So Q1 and Q2 are fixed particles, and Q has been brought from infinity. So the distance d is given. So this is 2d, this is d, and there is an angle that's been given, and theta 2 is 60 degrees. Alright, so it doesn't matter along which path it has been brought, because remember, all that matters is the final configuration and the initial configuration. And during the initial configuration, the capital Q was at infinity. So it's been brought from infinity to the indicated point here. And the question is, what is the amount of work that's been done? By the way, in the previous problem, I've missed one of the things. That is, I found out the potential energy to assemble the arrangement, but we were supposed to find out work. Remember, what was the work to assemble that charge configuration? And as you know, work is equal to negative delta U. In this case, delta U is U, so I should put on a minus sign here, right? And that should have been the answer. Okay, so a little caveat in the previous problem. Anyway, what about the current problem? So that's I'm sorry, this is 2d and this is d. So 2d might be a bit bigger. Alright, and a particle has been brought from infinity to here, so capital Q. This is Q1 and here is Q2. This angle is given, theta 2. This angle is given, theta 1. The question is, what is the work that needs to be done? So this is problem 50, I guess. Yeah. So we have to know the potential at this point, and then Q1 in the presence, right? So delta V would be equal to Q, I should say Q1, excuse me, I should say Q1. Of course, we have 1 by 4 pi epsilon naught. Then I have Q1 divided by 2d. Okay. Plus, again, Q2 divided by d. And then minus what was the potential at infinity. So the potential at infinity would be 0. So that's the V. Okay. What is also given is that there is a relationship between Q1 and Q2. So Q2 is negative Q1 divided by 2. Alright? So Q2 to negative Q1 divided by 2. So now, if we plug that in, we get, so you can just take d inside, 1 by 4 pi epsilon naught. I have, and then d, I have Q1 divided by 2. Instead of Q2, I have to write minus Q1 divided by 2, so this is 0. Since delta U equal to capital Q times delta V is equal to 0, this is also 0. So to bring the charge, capital Q, from infinity to the indicated point, you didn't have to do any work. Yeah, so that's the answer. That's the answer, because work is negative delta U, which is 0. So that's the answer. Next problem. This is the next problem, 59. A charged particle either an electron or a proton is moving rightward between two parallel charged plates. That's interesting. Separated by a distance. And the plate's potential are at V1 equal to negative 70 volt and V2 equal to negative 50 volt. Don't be worried because both are negative. It doesn't matter whether one is negative, the other one is negative as well. What matters is that if there is a distance between the two, if there is a difference between the two plates, between the potentials of the two plates. So there is a difference, and that's all matters, right? Because we can never find the potential absolutely at any point, because it always has to be measured with respect to the potential at the other point, at another point. So if there is no difference, then you can say both of them are at 0 potential, or both of them are at minus 100 potential. Both of them are 100 plus V plus 100 volt potential. It doesn't matter because only the difference matters. So for us, the difference between this one, so if I say this has 0 potential, this would have plus 20 volt potential. And then there is a particle that's been put here. The particle is slowing from an initial speed. Alright, so electric field goes from higher potential to the lower potential. So that's the direction of the electric field. And if the particle is slowing down, that means the force on the particle is in this direction. Right? Because the initial speed was to the left, so that's V naught. But it's been slowing down, so that means the acceleration is on the right side. And the acceleration is force divided by mass. But force is charge, either it's electron's charge or proton's charge, right? And then E divided by m. So if in order for it to be slowing down, yes, the acceleration has to be toward the left, and that means along the electric field. And the acceleration will be, the force and acceleration will be along the electric field. If the charge itself is positive, that means it has to be a proton. So that's the first answer, right? So number 59, the acceleration, which is equal to F divided by m, and the electric field are in the same direction, right? They would be in the opposite direction only if the charge is negative, right? Because why? Because F is equal to Q times E. So as you notice, if Q is positive, then E and F are in the same direction, which is the case we have just noticed. So therefore Q has to be greater than 0, so that means the charge is a proton. Okay, so that's the first part. What is the second part? What is its speed just as it reaches plate 2? So where does it start? It starts from the left plate with a speed 90 km per second. So yeah, let's find out. So the potential difference, delta V, should be equal to, remember delta V is given, we've just found out. So V right minus V left was equal to 20 volt. Do you remember? So V right was minus 50, V left was minus 70. So if you do the subtraction, you get plus 20. Okay, so this is simply integral over E ds, right? So from the left to the right. and this gives us ED, where D is the distance between the left and the right plate. So D is the distance between left and right plate, and that is going to be so E, we know E equals sigma divided by 2 epsilon naught. So notice this is the plate, right? So because of it, the electric field is sigma divided by 2 epsilon naught. 2 epsilon naught, I should say, in both directions. Alright. Because of the right plate, I should use a different color, and the right plate has to be negative because I'm sorry, the right plate has to be positive, this plate has to be negative. So I should change the direction of the arrows, right? Because yeah, that makes sense. Do you understand why it's negative and this one is positive? Because this one has, the right one has higher potential. That means it must have positive charge compared to the left one. So yeah, the trick I'm gonna use, we'll have to use once again. So this is the direction. Okay, of the electric field. Alright, now for the right plate, because it's positive, it's also going outward, right? So as you can see, these two electric fields are in the same direction, so they add up, and if they add up, then it's equal and opposite, so you should be able to get a 2 in here times D. So 2 cancels the 2, you have sigma D divided by epsilon. Do you understand why the 2 in the numerator came, the 2 in the upstairs? Because there are 2 plates, both have the same charge density, presumably, and both are contributing electric fields in the same direction, right? So the electric field add up because electric field is a vector, and therefore it's double of whatever you had for a single plate. Now you have 2 plates, the electric field doubles. That's why there is a 2. Okay, make sure you are clear about this. So that's V, and that's been given, right? This is something I'll mention again. So that's just a side calculation. But the important part is this is given. If this weren't given, then this would be the way you'd find it. Anyway, so the electric field, I'll need this here, delta V equal to this. So electric field equal to delta V divided by D. And if you multiply Q, E is the charge of the proton on both sides, then we have the force, right? And if you divide everyone by the mass of the proton, then you get the acceleration. So that's the acceleration. Okay, notice everyone is constant here, right? Again, this is just me showing you an example. So later when we'll try out potential and fields due to this configuration, which is exactly that, the configuration of a capacitor, right? You'll notice that delta V is exactly equal to that. So not particularly for this problem, but I didn't want to miss the opportunity to show you this, because the next time you see this, you'll remember it easily. So acceleration is E delta V divided by md. So we have E delta V divided by MD. And everyone is positive here. Everyone is constant, most importantly. It doesn't matter if positive or negative, it's constant. So therefore, what was the question? I forgot the question. The question was, what is its speed just as it reaches plate 2? Oh, alright. So for that, we'll need to know about this formula, v squared equal to v naught squared minus, or I should say plus, yeah, plus 2ad. And so v is going to be square root of v naught squared, and the acceleration is, compared to the initial velocity, the acceleration is negative. So I should put a minus sign here, right? Or this is confusing for you, is it? I should give a plus sign because I started with a plus sign, and then I can also put a minus sign here. So either you put a minus sign here and a plus here, right? Or you put a minus sign here and a plus sign here and then a minus sign here. Okay, but A always has to oppose. A is opposite in this circumstance. A has to oppose V naught. So that's why the relative signs has to be different. So minus 2 E delta V divided by M D into D. So D cancels, so it's just M. So that's the answer, right? This is speed, this is lowercase, this is uppercase. That is the answer. Next problem, 74. Alright, so we have three particles. Three particles are the vertices of an isosceles triangle. So that means two sides are equal, but the third side isn't. So we have an isosceles triangle, and I have Q1, Q2, and Q3 all at different charges, right? So notice Q1 is plus 10, Q2 is minus 20, Q3 is plus 30 in terms of microcoulomb. So all of them are different, are positioned at the vertices of an isosceles triangle. Alright. And A is given to be 10, B is given to be 6. That's fine as well. So all the Q's are given, A and B are given. How much work must an external agent do to exchange the position of Q1 and Q3? That's in problem number 1. And at problem number 2, you have to find out the work to exchange Q1 and Q2. Alright, so that's pretty interesting. Let's do that. Alright, problem 74. We have this triangle, right? So Q1 at this end, Q3 here, Q2 here. This is A, this is B. I'm sorry, this is A as well. This one is B. Okay, first we exchange Q1 and Q3. So we have to exchange the position of Q1 and Q3. Alright, what about, the question is, what does an external agent have to do? So the work done by the electrostatic force, right, is W equal to minus delta U, and this would be minus U final minus U initial. So that's by electrostatic, the work done by electrostatic force. Do you understand? I should write, the subscript should be capital A. The work an external agent has to do is negative of that work, right? So the external agent, WEXT, W write it with a different color. W ext equal to minus work done by the electric field. Right? The work you need to do has to be opposite to the work the electric field will have to do. And so we have UF minus UI. So we need to find out UI, which is the potential energy, starting with this configuration right here. Right? What is the potential energy? Then we'll have to calculate UF. What is the potential energy associated with the changed state after I have exchanged Q3 and Q1. Okay, so let's go to the next page. So again, B, A, Q1, Q3, Q2. So U initial for this configuration, what is that? It is 1 by 4 pi epsilon naught. Again, like before, first bring Q1, so you don't have to do any work. Then bring Q2, so it will have to be Q1, Q2 divided by B. Then, in the presence of Q1 and Q2, bring Q3. So this is going to be Q1, Q3 divided by A, because that's the distance between them. And then again, in the presence of Q2, Q3 has to do this work, Q2, Q3 divided by A. So that's the initial configuration. But with the final configuration, in the final configuration, Q3 is in here. Q1 is in here at the top vertex. Q3 is here, the bottom vertex. So I have my 4 pi epsilon naught. So now the role has reversed. First bring, so this is, I should, this different color, this is Q3 after the exchange, this is Q1 after the exchange, and Q2 sits where it sat before the exchange. So this is going to be, so first bring in Q3, so in the presence of Q3 you have Q1, so Q3, Q1 divided by A. Then you have in the presence of Q3 and Q1 you bring in Q2, so Q3, Q2 divided by A plus Q1, Q2 divided by B. Isn't that right? Or I'm making a mistake here. I think I'm making a mistake. So first bring Q3, then bring Q1. Okay. So in the presence of Q3 and Q1, then bring Q2. So Q3, Q2. Oh yeah, here it is. This should be a B, right? So the distance between Q3 and Q2 in the new position, it should be B. Okay, and Q1 and Q2, that should be A. Right, that should be A. Yeah, that seems correct. So W external, which is UF minus UI. So if I subtract this from that, what do I get? So I get this equals, well, the similar terms, if there exist any, will cancel each other. So I have Q1, Q2 divided by A. Q1, Q2 divided by B. Not similar. Q3, Q2 divided by B. Q3, Q2 divided by A. Not similar. Only these two terms are similar, so they cancel each other. So at the end of the day, you would find 4 pi epsilon naught. And then you have Q1, right, Q2, Q2, 1 over A minus 1 over B. And then you have Q2, Q3, so plus Q2, Q3, and then you have 1 over B minus 1 over A. Okay, so if you want to simplify it even further, then what you find W external equal to 1 by 4 pi epsilon naught. Then I have 1 over a minus 1 over b. So I factor out this from both. Then I get a minus in here. Notice this is negative of this. So yeah. So I have Q1, Q2 minus Q2, Q3. That's the answer. Just plug in the values of Q1 and Q2 and Q3 along with their signs, of course, right? We have considered everyone to be positive, but as you can see from the question, they're not. Q2 is negative. So be careful when you plug in the value. Plug in the signs as well. Signs has to be proper. Okay, what about the question number B? B can be done similarly, and I think you can do it on your own now that I've solved number A for you. Okay, let's go to the next problem. Okay, last problem is 83. Alright, so what about 83? 83, here we have point P at a distance D1 from Q1 and D2 from Q2. Both particles fixed at the place, so Q1 and Q2, they don't move. With V equal to 0 as infinity, what is V at P? Well, that's easy. That's Q1, 1 by 4 pi epsilon naught, then Q1 by D plus Q2 by D. If we bring a particle of charge Q3 from infinity to P, how much work do we need to do? Just multiply that charge with that potential. And what is the potential energy of the 3-particle system? That's pretty easy. It's very easy. So let's do that. So let's go to the new page. Yeah, so 83, right? Yeah. So this is D1, this is Q1, this is D2, Q2, this is P points. So question number A, what is the V at P, given that V at infinity is equal to 0? So it's pretty simple. So V at P is simply going to be 1 by 4 pi epsilon naught, and then you have Q1 divided by D1 plus Q2 divided by D2. End of story. Bring a third charge Q3 at point P. What is the work? So work done to bring a third charge at point P. So point P is going to be 1 by 4 pi epsilon naught. Then you have Q1 divided by D1 plus Q2 divided by D2. Then you have to multiply the charge Q3, and so that's the potential energy, and you'll have to put a minus sign here, right? That's the work. What is the work that needs to be done in order to assemble the whole system? So Q3 here, so you need to consider all the 3 terms. So you have C, so W, in order to assemble the whole configuration, it is equal to I have to be precise, 1 by 4 pi epsilon naught, right, with a minus sign, and you have Q1, Q2. What is the distance between Q1 and Q2? It's square root of D1 squared plus D2 squared, right? So square root D1 squared plus D2 squared. What about Q1 and Q3? That's just D1. Q2 and Q3, The distance between them is just d2. That's it. That's the answer. And that's the end of this chapter. So I hope you have learned something. I have taught you something. Remember, this will need them in future as well. So make sure you understand them properly and make sure you are well adept at them so that you can solve them quickly in your exam. I hope this worked.